All right, let's get started. So, two quick reminders today. This is the last day to submit a project contribution. If you've been working on a project contribution, make sure you create your pull request and also fill out the form in the project contribution doc. If you don't fill out this form, I have no way of knowing that pull request is associated with you, so I wouldn't know who to give points to, and so I won't grade. I won't grade anything without a form submitted. So make sure you're submitting that form if you have a pull request, if you've done a project contribution. Uh, and the other thing, if you go to one of the top posts on Piazza, hopefully you're all aware of this, but who are interested anyway. This Sunday is the last day to apply if you want to be a 115-116 TA starting in the fall. So if you're interested in that, if you've been thinking about it and saying maybe you've been working on your resume or whatever, make sure you get that in. Make sure you get that in on before Sunday. And then next week, we'll start looking through the applications. Interviews will be during finals week. So we have 2 weeks to look over the resumes, send you invites for interviews. You can get started on your interview early if you want to know what it's about. Is you'll have 10 minutes to teach us a 115-116 topic of your choice. So you can teach us about loops, conditionals, recursion, as one brave person in chat is going to do. Object-oriented programming, whatever you want to teach us. Teach us for 10 minutes, and then for 5 minutes, we'll ask you questions. And by we, I mean myself, a few other faculty members, and current TAs. There might be a pretty big group of people there that you have to teach to. And then we'll decide whether to give you an offer or not. So hopefully I'll see a bunch of you applying and interviewing. Applications were pretty light from this section. We have quite a few applicants total, but from this section, I think there were only like 8 last time I checked, which I guess isn't too low of a number, but still. There are more than 8 of you who make good TAs. So if you're on the fence about it, I'd encourage you to apply. We have a problem, and I was just talking to a student about this, is there's one... do I want to do this whole speech? I don't think I've done this yet this semester, or at least not recently. But imposter syndrome is a real thing. We have a lot of students who I know would make fantastic TAs, who are afraid to apply because they don't think they'll make a very good TA. Get all that nonsense out of your head. Seriously. And here's a good rule of thumb. If you're questioning, oh, he's not talking about me, I'm actually terrible. If you have the self-awareness to even be doubting yourself at all, you're going to make a good TA. You're going to be fine. Just having that wherewithal to be like, am I, have that self-reflection, the fact that you're capable of having imposter syndrome, you're going to do fine. You'd be a good TA. Get your application in. Let us get a chance to give you an offer. And do that. We have tons of really good students who would make fantastic TAs who end up not applying because of that. Usually when we're in person, I'll reach out to you directly and target you and be like, you're going to apply to be a TA because you're going to be great. Oh, I don't know. Do it. Rin can attest to that. I've told that story earlier. Just apply. Don't let your doubt get in your way. Apply. I've had some of the best students I've ever seen have imposter syndrome and be worried about applying. Just apply. Do it. If you're interested at all in being a TA, apply. Let us decide if you're good enough, and you're probably going to be if you're thinking that. It's usually the students who don't think that at all, who think they're the best thing that ever graced this planet. Those are the students who usually don't get offers and don't get, don't have that self-reflection, that are a little delusional. If you're capable of imposter syndrome, you're probably doing just fine. With that said, I didn't think I'd give that mini speech today, but with that, today is going to be, and we get pizza next semester we'll finally be on campus again, and TAs usually get pizza fairly often, so if that sways you towards being a TA. So today is going to be tree examples. I've covered all the content that I want. There's no slides for today. There's no lecture task for today. The next lecture task will actually be next Wednesday. The for LT5. You actually be able to do LT5 and 6 with this, but I'll introduce LT6 right here, just like I did last week. Introduced an LT in the slides. I'll do that same thing next Friday as well. There won't be any slides. Next Friday will be examples as well. So today is examples. I'm going to go to the repo. I'm going to run the debugger on the tree examples in the repo and show you like how that's working and just give more explanation about what's going on with those trees. So while I'm doing that, chat, if you got questions, if there's specific things that you'd like to see, what I have planned is I'm going through the, which one is it? This one? I'm going through the examples in the repo. And once I'm done with that, I'm going to go to LT, I guess AO2 technically. The code that I provide for AO2 and talk about how that plays into this, how this uses a tree. And I'll talk about LT4 a bit, how LT4 is going to use this code. Or how it does use this code, rather. So that's what I have planned. If there's something else that you think would be helpful, let me know. Let me know and I can pivot, adjust. I'm here to help you understand trees today. That's my job today. The hiring cycle for UTAs is for fall. We always do our hiring at the end of each spring, and then we'll hire you for the fall. If you want to defer, did somebody ask about this? Where did this? Were we able to be a TA next spring? So if you want to, like if you get an offer, you can say, I don't want to start in the fall. I'd like to defer until the spring. You can do that. But we only hire at the end of each spring semester. We don't hire, we don't have another hiring season. We don't have 2 hiring seasons per year. We only have 1 hiring season. So if you want to start in the spring, apply now. And then if you get an offer, say, I'll start in the spring. Which is pretty common for employment too. If you get an offer, you say, okay, cool, but I don't want to start right away. I'd like to take a month first and do that. I did that with an internship before. I got an offer for a summer internship. And I said, I don't want to do an internship in the summer. I want to do it in the fall. And they're like, sure, whatever. Most employers are very accommodating with things like that. And we're no different. If somebody wants to hire you, like they're committed to you at that point. You start calling the shots once you get the offer. It's the only time your employer really has a lot of power is before the offer. Once you get that offer, they're committed. That's true like across the board. They're not going to rescind an offer. Can we see an example of a binary code in code? I assume you mean binary tree. Yep, that's what most of today is focused on. So let's get to it. I can't zoom in on this? So what the hell? There we go. Okay, so let's see an example of this. I'm in the examples repo. You have this code if you want to follow along. I'm in the LO4 trees binary search tree example. I'm going to start with the binary search tree. Computer enhance. I have a main method that just calls my examples. Am I going to go through example 2? What even is the difference between these? Oh, that's my crappy one that turns into a linked list. We're not going to do example 2. But we're going to go through example 1 and just talk about what happens when this code executes. So we give this binary search tree a comparator. We create the binary search tree. We insert a bunch of values into it, and we find a particular value. And I'll show you in the debugger what's happening in memory and how this executes, how this whole thing executes. A few notes before we hit that. A binary tree node. This is right from the slides. Come on, I just did this. How did I do that? There we go. This is right from the slides. A binary tree node takes a type parameter A. It has a variable of that type, the value that it's storing, and references to 2 more binary tree nodes. It's left child and right child. A binary search tree. That works like half the time. A binary search tree takes a comparator, a type parameter, and a comparator in its constructor. And then it's going to organize the tree based on this comparator and store values of type A. It has one variable aside from the comparator. The root of the tree It's going to store a reference to the root of the tree, which is a binary tree node of type A. It's going to initialize it null because initially the tree is empty. And when we insert, if the root is null, that's the first node. We set the root to that node. Else, we're going to use some recursion and find out where to insert that based on our insert algorithm, which we're going to see plenty of examples of. I'll explain this code more in depth, review this code more in depth when we call it. And also find, it runs through the same decisions as insert based on the comparator. If A comes before the value, go to the left. If the value comes before A, go to the right. Otherwise, we found what we're looking for. So that's the code we're looking at, and we want to run this thing in the debugger. Binary search tree example. Yep, that's the right one. Let me catch up on chat. Yeah, next semester is a big workload. There's no sugarcoating it. Next semester is a rough one. Oh no, I don't think I can zoom in on the debugger. Nope, I'm on the wrong window. Of course, it only works like half the time over here. Yeah, I can't zoom in on that. That's a bummer. AI, binary search tree example. Better. Okay, bigger, better. Everyone happy? Everyone can see that? We can drag debugger all the way up. Yeah, you can. I'm trying to utilize my space though. You can drag it all the way up, but that doesn't resize the text if that's what you're talking about. Yeah, and we can put the. It doesn't want to right now. You know what? I don't want to mess it up, so I'm not gonna mess around with it. All right. And can I just delete these things? Remove watch. I've had these on here all semester. Is that all I had to do? I had those on a watch. I didn't even know I could do that. All right. Man, I wish I did that a long time ago. That was super easy. So we have a main stack frame, just a very quick recap of stack frames. We have a main stack frame, which called example, that put another stack frame on the stack. This is a stack frame that we're in. The stack frames, I don't think I made this connection super clear during the stacks because I got it in office hours, so I was happy to be able to explain it. I must have missed this in lecture. I just gave like a one-liner on it. But the stack, the memory stack, is the same as the data structure type stack that we talked about. It's a last in, first out data structure, and you can only access the top stack frame. So you can think of the memory stack as a stack of stack frames. So we put frames on the stack, and we can only access the frame on top of the stack. Any variables in lower frames, lower down on the stack, we can't access those. We can't access args anymore because the main stack is not on the top of the stack, or that stack frame is not on the top of the stack. So we can only access the frame that's on the top of the stack. Similar to our exactly like the stack data structure. We can push to the top of the stack, we can push new stack frames, we can pop the top stack frame, and we can work within the top stack frame. But we can't go rummaging through the rest of the stack. We can only work with the top stack frame. Right now, the top stack frame, the method that's executing right now is example. And let's start stepping through this thing. Debugger everywhere. Yeah, this doesn't really help us. Like, this won't make the example more clear. We can do it. So let's start stepping through this. So first thing, we create a first order function, int less than, which is our comparator. This is a value that's a reference to a function that takes two ints and returns a Boolean. So the type of this int less than variable is a function that takes two ints and returns a Boolean, and it's equal to the less than operator. So we're doing the standard just less than operator. Oh yeah, course evals started today. Do your course evals. I'm going to have, I don't know what my incentive is going to be for this course, but I got to come up with some incentive to bribe you to fill those out. Fill out your course evals. So this is going to be the less than operator. This is a function that takes two ints and returns a Boolean if A is less than B. One AO. I'm too generous on the application objectives already. I don't know about definitely not a free AO because I already gave you free AOs. Usually it's you have to complete one AO just to get a C minus. Right now I'm already on 0 AOs to get a C. So I effectively already gave you 2 AOs for free, which maybe I shouldn't have done that and just waited for the course evals and then said, oh yeah, I guess I'll do that if you get a certain percentage, instead of giving it to you without you having to work for it. But I already gave it to you, so I can't give another one. C plus or C plus being the lowest grade you could get in this course. Pass the course. The problem with that is a lot of you are going to pass the course anyway. So doing anything with the LTs is tough because it doesn't motivate anybody who's already passing. I've actually had students in the past who are like, that incentive doesn't affect me anyway because I'm already going to get an A. So I'm not going to do the course eval just to screw those people over because those slackers get what they deserve. I've actually had students with that attitude, which I assume a lot more students have the attitude than I know about. But I actually had somebody say that to my face. Like I'm intentionally, I actually want to give you the feedback, and they were giving me the feedback right then. But they're like, I'm not filling out the form because I want to sabotage them. It gets crazy. Things get crazy with that. But at the same time, I understand where they're coming from. I wasn't happy, and I expressed my displeasure with them. But I'll come up with something. I don't know what I'm coming up with yet. I know what I'm doing in 312, but I haven't decided with this course. With a percentage-based structure, it's a lot easier to come up with an incentive. You just throw a few points their way. But with this course structure, I'm not quite sure. All right, so let's get through this. Let's start doing this. Oh, so we have this function. Functions are just regular objects. This isn't something that I, like, if you didn't do this on the last quiz, I didn't worry about it because I didn't really talk about it. But since a function is an object, int less than is a reference to an object that's on the heap, which is a function. So this is a function. We can tell from this at 824 that it's an object on the heap, and that int less than is storing a reference to that object. It's actually a lambda function, comes from lambda calculus, and borrows some of that terminology. But we have a reference to a function that's on the heap. So let's go into our constructor. We're going to create a new binary search tree with this comparator. So when we create this binary search tree, our comparator is going to be that same function at 820. What did I say? At 824. It's going to be that same function. That's what comparator is going to be once we call that part. Comparator is going to be that function at 824, which is the less than. We can't really see it in here, but it is the less than function. Root is set to null, and we're on our way. So we have a binary search tree that has that comparator and the root of null. Extra credit. What's the name of my dog? You have to spell it right too. That'll get a lot of you getting it wrong. First page should just be pick up Kobe. All right, so let's insert the value 5. We're going to call insert 5. Check if root is null. So this dot root, it's null. So root is going to be a new binary tree node with the value 5 and no children. So we go into that constructor. We have 5 null null. For this particular binary tree node, A is int, and value is going to be 5 for this constructor call. So we return the new binary tree node, set root equal to that. So root gets that new node, which happens to be at 847, or 47. I can do this. I know what numbers are. At 845 with a value of 5 and no children. Let's get into the next one, inserting 2. Root is not null, so we're going to hit our recursive helper here. We're going to give it the value we're inserting and also the root of this tree to start looking for where we want to start searching for the place to insert this thing. So we're going to go into insert helper where A is 2. Node is the root of this tree. The root of this tree is the node at 845. Node is the node at 845. So we have a reference to the root of the tree, a reference to that exact same object on the heap that has the value 5. We're going to call our comparator. Our comparator comes into play, which in this case is the less than operator, and check, is the node's value that we're considering, does that come before A, or is node.value less than A? So node.value is 5. We're calling 5 less than 2. That's false. So we're going into the else. Oh yeah, we actually get, I briefly mentioned this, I think, at some point. But we do put frames on the stack for our function calls. So we actually go into this code, put a frame on the stack for that function call. We have our A and B, 5 less than 2. And we can see our function call. One of the rare times we put a function call on the stack as opposed to a method call, which are actually represented by methods if we're really looking into Scala, but we're going to pretend they're pure functions. So that returned false. So we're going into the else. And this means that we're going to look left. If that were true, we're going to look right. It's false, so we're going to look left. And we're going to try to insert this to the left. If the left node is null, which node.left is null right now, our entire tree is only one node. So everything else is null. So we're going to look left. We don't find anything. So that means we've found where we're going to insert this node. Since left is null and we're looking left, that's where we're going to put this thing. So we're going to create a new node with the value 2 that we're inserting. And then set that equal to this node's left value. That line doesn't, I don't know why the debugger does this. This line doesn't actually get executed, but the debugger makes it seem like it is. That returns back to the insert method, and that's going to return back to the example method and move on to the next line where we're inserting 8. So at this point, our binary tree has a reference to the root, which has a value 5. It has a left child containing the value 2, and everything else is null. So we have 2 new nodes in this tree. Blitzkrieg Impostor Syndrome is running rampant in me. Then you should apply it to be a TA, according to my logic earlier, right? Apply to be a TA. When I say it that way, the logic doesn't really make too much sense, but I'll stand by it. Any questions on this so far? I haven't seen any questions in chat, so if I missed any. Rin, that is not exactly helpful. Okay. This material is understandable. Thank you. I felt like I was talking to myself for a bit there. This material is understandable. Cool. So let's do insert 8. I'm going to pick up the pace a little bit then. Root is not null. We're going to hit the else. Go to our helper method. Start at the root. Let me expand this a little bit. We're going to start at the root. This at 845. That's what our node is for this call because we gave it this dot root. So the root 845. We're going to check that value. 5 less than 8. Node.value A. Node.value A. That's going to call our function, put that frame on the stack, and call this with A and B of 5 and 8. That's going to return true. If I know my arithmetic at all, which I can't even read numbers earlier. So we're going to look right. We're going to find null. So we're going to insert a new node with the value 8. And insert that as the right node of our tree, of our root. So now the root has 2 children, left and right, with the left being 2 and the right being 8. Let's insert 4. We're going to start with the root. Is this code modified to always create a balanced tree? Yeah, the order in which I'm inserting the nodes was carefully chosen to make sure it ends up being balanced. If you want to see one that doesn't end up being balanced, maybe I will just run through this one. The next one, the other example in this code, make sure that it's not going to be balanced. This will create effectively a linked list where every child is to the right. But I just carefully picked the order in which I insert these to make sure that it ends up being balanced. Too scary. Yeah, thanks, Ren, for that. Now that one was helpful. So right now the root has the value 5, left and right child, where the left has 2 and the right has 8. And we're looking to insert 4 at that point. Right now the node we're considering is the root. We're going to check the root's value. Is that value less than 4? No, so we're going to look left. Left is not null this time. So since left is not null, we're going to recurse. We're going to call insert helper on the left child. So this node's, the root, in this case, left child, at 857, which contains the value 2, we're going to recurse on that node and call insert helper again. So now insert helper is called on that node at 857. If we look at our entire tree, we have the root node, we have its left node, we have its right node. Right now we're on this left node of the entire tree. That's the node that we're currently considering at this point. We're going to say 2 less than 4, which better be true. The right node is null, so that's where we're going to insert this new node containing the value 4. And now we have the root's left node, its right child, is now a node containing 4. In the debugger, how do you return to your code from Scala codes and the breakpoints? So if you end up getting deep into a Scala library, do this step out, and that's going to help you get out of that stuff. Like right now, I'm in a method call, insert helper. If I do step out, no matter where I am in this method, step out is going to go to the end of that stack frame. Whenever that stack frame ends and returns execution back to the previous stack frame, that's where it's going to take me. I happen to be at the end anyway, but I'm going to click step out. That's going to kill this stack frame, go back to this one. That's going to take me to insert. I'm going to do step out, and that's going to take me back to the previous stack frame again. So if you end up getting in the library, click step out until you get back to your code. Yeah, thanks repetition for the assist there too. I should have just said read repetition's comment. Was that? Oh, I thought that was a 3. I'm like, was that 10 minutes ago? I thought the time was 2:33. So let's insert the next one. It's kind of on repeat at this point. We're going to insert. The root's not null. We're going to call insert helper. Insert helper on the root. 5. And our tree's getting bigger here. The node we're considering currently is the root. 5 less than 7, true. So we're going to look left. Or, sorry, we're going to look right. The right node is not null. It is, in fact, a binary tree node with the value 4. So we're going to recurse on the next node, on the right node of the root. So now node is going to be the right node at 870. If we look at this dot root, where this is the current object that's calling this method, the current binary search tree, root, its right node is at 870 with the value 8, left, right of null. So node at 870, 8, null, null. We're going to look where to insert 7. We're going to look left. That's null. So we're going to insert it to the left of that node with 8. And worth mentioning, just a quick reminder, as soon as this line executes, node.left equals binary tree node. Quick reminder of references. We have a reference to node at 870. When we make that change, when we say node.left equals a new binary tree node that we create with the value 7, that immediately changes this dot root. That immediately updates this dot root, that tree, that overall tree we're building, because the root's right value is the node that we were working with, and we were working with it as a reference. We had a reference to that node. So when we say node.left, we go to the value 8 at 870 in the heap and make a change to that object. So outside of that method, we see that change. The overall tree we're building does get that node added to it in the overall tree that we're building. So a quick reminder, hopefully everybody's good on that stuff. Please ignore your previous message. Well, now I have to read it. Me keeping track of Discord chat and Twitch chat. No. And then return. We're several layers deep in recursion. We had quite a few frames on the stack. 14, just to show off some more debugger, and because this is getting pretty repetitive, I'm going to step over. So if I do step into, that's going to go into this method call like we've been doing. Step over is going to skip right over it. For some reason, it skipped over everything. Where did I end up? So here, like I'm in Scala code now. I'm going to do step out to get out of here. We get back to our code. I actually don't know where I ended up there. Insert example. How did we get there by doing step over? I don't know how we got into that world. That was like an alternate dimension there. I'm going to try it again to see what happened there. So I'm trying to step over that method. It goes into here, maybe because I have the breakpoint set. It might be because I have the breakpoint set. And then I want to get to the find. You know what? I want to rerun that to make sure that it was because of the breakpoint. I think it was stopping at the breakpoint. Oh, well, now I need that breakpoint though. Yeah, it's because I had the breakpoint set. So that skips over the method call that we don't want to be concerned with. So after all those method calls, BST root, we get this whole tree. And it happens to be the same tree that we saw in the slides. before, and it is a balanced tree. So let's find something in this tree. We're going to call find. Find immediately calls find helper on the root. Find helper is going to check if the root is null, which it is not. So this is a reference to the calling object that has a root variable. That we passed a reference of that to node. So node right now is the root. Oops, wrong one. Is the root. Same reference. So node right now is the root. We have 5. We're looking for 14. 14 is greater than 5, so we're going to look right. 14 is greater than 8, so we're going to look right. And then we find 14 there. That's what we expect to happen here. So we're going to use our comparator. Is A 14 less than node.value 5? No, so we're going to hit the else if node.value less than 14, true. So we're going to move right and make a recursive call. We're going to move to the right node and pass a reference to that right node to the next recursive call. So now node is at 843. If we go back to, I flattened out my root. Its right node is 843. So we have a reference to that right child of the root. That has the value 8, so we expect to move right again. Hit the else if, move right, recursive call that on root.right. We moved right again, so we expect node to be at 846 right now, and node is at 846, which has the value 14 now. So now we're going to check, is 14 less than, 14 less than 14? No. Hit our else if. Is 14 less than 14? No. Because they're the same. That's the only way both of these can return false, is if they're equivalent compared to this, according to this comparator. So we hit our else, and we're going to return this node. This is the node that contains the value that we were looking for. So we're going to return that up this recursion. Notice how we're several layers deep in our recursion. We're going to return from this stack frame, return from this stack frame, return from this stack frame, and we're going to return that node that contains the value 14. This at 846 is returned. We don't do anything with it. We just leave it on the ground and walk away. But that's what's returned from that method call. Oh, y'all are negative. Can't wait to fail the quiz. Your brain cells are dying. What is this madness? Y'all weren't asking any questions. The only comment I got was, this seems straightforward. Now after I'm done, you want to ask questions? Come on, Blitzkrieg. Unless you're talking about something else. Maybe you're talking about something else. I'm not going to answer the stack and heap question again. The number of times I've gotten the stack and heap question, I think I will end up putting it on LO4 quiz and interview. I can't believe so many of you are asking that. Stack and heap should be second nature to you right now. The fact that so many of you are asking about it means it's not second nature, and I have to test you on it again. You got to stop asking about that. You should know stack and heap by now. Yeah, Rin, that's what I'm thinking looking at it now. I think Blitzkrieg was confused with your how much debugger can a debug. I haven't even been paying attention. Well, if you're not paying attention, then the quiz should get harder. let's run this one more time with the other example. Since we're here, I might as well run this one, but I'll go a bit quicker through it. So now we're going to insert -3, that's the root. 2, that's going to go to the right because it's greater than -3. 4, I did that again. 4 is going to check the root. Actually, let's expand this. Let's rearrange things a little bit here. BST root. We have -3 at the root, inserted 2. We're going to insert 4. It's going to check the root, go to the right. Check 2, go to the right, and insert to the right. 5, -3, go to the right. 2, go to the right. 4, go to the right. 7, -3, go to the right. 2, go to the right. 4, go to the right. 5, go to the right and insert. 8, you get the idea. It's just going to keep going to the right, to the right, to the right, until our entire tree is effectively a linked list, where all the left children are null, and all the right child, like that's where all the content is. And then to find, we got to go to the right, to the right. Well, you know what? I don't want to belabor that point. Oh, we're up against it on time. All right, how do I, now that I'm sharing it like this, want to carefully resize this thing. Switch to this. Get it like that, and it's good enough. So I can talk about this stuff. Let me make sure that's the right thing. Okay. So in AO2 and LT4, these are the places in the project where we're working with trees. So I want to explain this just a little bit. I got no debugger to run here. But I want to explain this just to make it clear what's going on here. So this starts at the AI actor class, which calls both the decision tree method and the make decision method, and takes the current game state. So we're getting the decision tree from the AO2 code, and then calling your LT4 code to decide what action is going to be taken on that decision tree. This decision tree is of type, let me jump around a little bit. The nodes are of type decision tree value, which have 2 methods, check and action, each which take an AI game state. Check returns an int, which tells you how to navigate this tree. If you check a node and check, given the game state, returns a negative number, you want to recurse and go left or loop. Some of you have been looping. And if it returns a positive number, you're going to go right. And if it returns 0, this node contains an action. It should sound familiar to the JavaScript comparators when you did sorting in JavaScript in 1.15. So if this returns 0, then what you want to return is the action. That means this node contains the action that you want to take, that the AI is going to take. And this is the decision tree is deciding what action is the AI going to take on this update of the game. And the game updates 10 times per second. So 10 times per second, the AI is going to decide what action should I be taking right now. And we're doing that with the decision tree. So if this returns 0, that means you're at an action, and then this action method is going to return the action. There's 2 types of nodes that extend this decision tree value. Either a decision node, which takes a function that takes in the game state and returns an int, and that's going to be called on check. So when you call check, it's forwarding the functionality to that function and then returning an int. And action, I actually updated this. If you have older code, if you pull or just add this AI_0 here, there's actually this should never be called, as the comment says, but there's a certain way that you can code this where this does actually get called, and it's not like a ridiculous thing. It's something that, it's not the worst thing that students do that end up getting this called. So I just added something that doesn't break things. But if you get an empty player list and you don't have the latest code, put AI_0 here, or pull the repo and get that code. So a decision node, action should never be called. I just have some default value here for the action of if this ever happens to be called. And then action node, this is what's actually going to return an action. So check is always going to return 0, saying this node is designed for Jesse pulling his own repo. That's a pretty common thing. The most pulling you'll do in your life is your own repo, in all likelihood. It worked fine for you before AI_0. It depends on exactly how you code it. There is a way to code LT4 that's not wrong, but also breaks and ends up calling that. But if you didn't code it that way, then you're fine. So this returns 0 because the action nodes are made to be actually returning the action. And then the action, this also takes a function in the same protocol, will return whatever that action says. That's what the AI is going to return. The AI actions can either be moving the player, stopping the player, firing in the direction that you're facing, or firing in a different direction than you're facing. Those are the different actions an AI player can take. So this decision tree, which is intentionally a mess because I don't want to give away the solution to AO2 too much, but we're going to create a binary tree node that's an action node. This action is going to hunt the closest player. This calls a lot of your code from LT1 through 3. We're going to locate a player. We're going to locate the player that this action, the reference player is the player that's taking the action. We're going to locate that player to get their location. We're going to locate the closest player to them. We're going to compute the path from this player to the closest player. We're going to use that path to find out what direction we need to move towards, what direction we need to move in. And then we're going to move. So if we decide that we're going to take this action node and move towards the closest player, we're going to take the action of moving the reference player towards the closest player by getting a path to the closest player and then moving in that direction. Once you do AO1, you can replace this compute closest player and compute path with your LT6 and AO1 code instead, and have the AI avoid walls once you update this. So this node, this is an action node. If we're taking the action, if we want to take the action of hunting the closest player. We also have a fire node where we just fire in the direction that we're moving. And then one decision node, which is going to ignore the game state and then use math.random to 10% of the time fire as the left child and 90% of the time hunt the closest player. So in your LT4, you're going to get this decision tree where the root is going to be in your GUI anyway. I have different trees set up for testing. The root is going to be this decision node, which is either going to return -1 10% of the time and 1 90% of the time randomly. If it returns -1, you're going to travel to the left node, which is an action node. So when you call check on it, it's going to return 0. Check is going to return 0. And then when you call action on this, it's going to return whatever this function returns. This is one big function, by the way. It's going to return whatever this function returns, which is going to be move player in the direction, move player towards the closest player to this player, without avoiding walls the way it's coded right now, because it's calling your LT 1 through 3 code. And if it returns a -1, you're going to go left. Did I say that backwards? If it returns a 1, you're going to go right and call this function. That's going to tell you what to do. And if it returns -1, you're going to go left, which is the left child of this node is a node containing an action node that just returns fire. So the function for this node just returns fire. You don't see any actor in AO2? The actors are... This is the only actor that touches your code. AO2 is this method. So when you do AO2, you're going to replace this code with code that takes actions based on... Instead of just randomly firing and hunting the closest player and running into walls and just getting stuck on walls immediately and firing into a wall, which is what these AI are going to do. Instead of that, after AO2, you should have a bit smarter AI that are going to make more informed decisions. You don't have to write any actor code. No repetition. All right. Oh, we're 4 minutes over. So bye, YouTube.